Here's one more example of a function where we're finding concavity and inflection points. This time the function is a natural log function. F of x equal natural log of x squared plus 1. Now, we need to find the second derivative. Okay, so, make a point of that each time because concavity depends on the second derivative, doesn't it? So we need to find f double prime of x. And so we start out looking for the derivative of f itself. Okay, so f prime of x is the first thing that we need to find. Now we've got to remember how we find the derivative of a log function. Remember, it's 1 over the argument. So it's 1 over what we're taking the natural logarithm of, and then we multiply that with the derivative of the argument, x squared plus 1. So we end up with f prime of x being, let's see, 1 over x squared plus 1, and the derivative of x squared plus 1 is 2x. So the first derivative ends up being 2x divided by x squared plus 1. Okay, now let's use that information to find the second derivative. Now in this case, before we had a fraction and we changed the form so we wouldn't have to use the quotient rule to find the derivative. But I think in this case that would probably not be that beneficial. So let's go ahead and use the quotient rule. Now remember how the quotient rule goes. The second derivative will be the denominator times the derivative of the numerator. Now in this case, the numerator is 2x, and so the derivative of 2x is just 2. And then it's minus the numerator, which is 2x, times the derivative of the denominator. Well, in this case, the denominator is x squared plus 1, and that derivative is 2x. And then remember, we take the denominator, which is x squared plus 1, and we square it for the denominator of the second derivative. Now, this is going to require us to do a little bit of simplification. So let's go ahead and look at that numerator again. Whoops. And notice that in the first part, we have an x squared plus 1 times a 2. So that would end up being 2x squared plus 2, wouldn't it? And then we have a minus 2x times 2x, which is minus 4x squared. And of course, that's all over x squared plus 1 to the power 2. And then we notice that, look, that 2x squared minus 4x squared is negative 2x squared. So the second derivative looks like it would end up being, let's see here, 2 subtract 2x squared, wouldn't it? Over x squared plus 1 to the power 2. Okay. Now we're ready. Okay, that kind of separates. Now we're ready to find critical numbers. So find the critical numbers of the second derivative. Now, let's discuss that from this point of view. We want to know where the second derivative is 0 or where it's undefined. And let's look at that fraction. Here's where I'm looking, right over here. When we look at that fraction, the only way a fraction is going to be undefined is if its denominator is 0. And because we have an x squared plus 2, and that's being squared, what we're worried about is is there a place that x squared plus 1, excuse me, x squared plus 1, is there a place that x squared plus 1 could be 0? Well, any value we put in for x, any positive number, would just get positive plus 1, and that's not going to be 0. Any negative number we put in for x would get, when we square that negative number, we'd get a positive, so it's positive plus 1, and that can't be 0. And I guess we could put a 0 in for x, but if we do, we square 0, we get 0, so 0 plus 1 is not 0, okay? So there's no x value that will cause x squared plus 1 to be 0, so there's no way this denominator can be 0. So there's no place the function's undefined. Now there is a place where the function could be 0, so the derivative. So what we're looking for is the solution to this equation. Where is the derivative equal to 0? And we've discussed this before, that the only way a fraction can be 0 is if its numerator is 0. So we want to know where 2 minus 2x squared could be 0. That's really what it boils down to. I mean, even if we multiplied both sides of the above equation with the denominator x squared plus 1 squared, when we multiply on the left side, we just get the top, 2 minus 2x squared. And when we multiply the right side, the right side's 0. And so when we multiply that side by anything, we'll still have 0. So we get this second equation that we're looking at no matter how we approach the problem. Now, we can do this one of two ways, but we can factor this left side. We can use, remember this is a quadratic equation. We can factor it and solve it. We can use the quadratic formula, or because this is a special quadratic equation where there is no x to the first power term, then what we can do is we can solve for x squared and then solve for x. So what I will do here is I will add 2x squared to both sides, so it will look this way. And then I'm just going to turn that around because I like it to look that way a little more. Then I'm going to divide both sides by 2. And when I divide on the left by 2, I get x squared. And when I divide on the right by 2, I get 1. And then I have to remember that anytime I have an x squared, then it's more likely I'm going to have two solutions. And so in this case, we actually get x is plus or minus. That's our two solutions. The square root of this number 1. But of course, the square root of 1 is just 1. So we get two solutions plus or minus 1. What does that mean? Two critical numbers of the second derivative. Two critical numbers. Okay? So now as we begin, I always get myself in a little bind here with space, don't I? Okay, so these are the critical numbers. So this thing might change concavities twice instead of once. Okay? So the way we think through this, recall, is that we're thinking of the x-axis more or less. And we have a critical number of -1, and we have a critical number of +1. And so we basically have an interval from -infinity to -1. And then we have an interval from -1 to +1. See, -1 and 1 break up the real number line into 3 parts, don't they? And then we have an interval from 1 to infinity. So it's in these intervals that we're needing to test the second derivative. It's these intervals that are of interest to us. So we're going to test the second derivative in each of these intervals, and then from that test, we're going to decide about concavity and inflection points. So we want to know about the second derivative. So we test a value, okay, and I really need some scratch paper, don't I? We test a value that is in that first interval from -infinity to -1. Well, a -2 would be an easy value to test, wouldn't it? So I'm going to test a -2. Okay, now here's what we get from that test of -2. We're going to put that -2 into the second derivative. Now, I'm a little bit lazy from the point of view that I want to think things out rather than do all the hard work. Notice in the denominator of, well, I tell you what, let's just put this value of -2 in and then we'll discuss it. So for the x's in the second derivative, we're going to replace the x's with a -2. So on top we'll have 2 subtract 2 times -2 squared. And on bottom in parentheses, we'll have a negative 2 squared plus a 1, and then we're going to square that. So on top, we end up with, don't we, 2 minus 8. Isn't that what we'll get? When we square negative 2, we get a positive 4, and 2 times 4 is 8. In the bottom, we'll end up with, well, 2 squared, negative 2 squared is 4, and then we have a plus 1, and we're going to square that. And so we end up with what? Negative 6 over 25. Now, we could have made shorter work of this if we would have noticed that the denominator is always going to be positive. We discussed that a while ago. No matter what x we put in there, the denominator is always going to be positive because we're going to square the result of putting x in there. And then we're going to add a 1, and then we're going to square that result. Now, the numerator might change because we're subtracting things that we're putting x's into. So we could have the numerator change on us, and we need to be aware of that. But in this case, we have a negative result. And that's all we want to, that's all we care about up here, is that the second derivative is negative. So that tells us the graph of the function is concave down. Okay, now we look in the next interval, x equals 0. Okay, and in that next interval, we're going to try x equals 0. It's in that next interval. So we put 0 into the second derivative. Okay? Well, we already discussed that when we put any value into the denominator of the second derivative, we're going to get a positive result. So let's make short work of that. Now, when we put an x of 0, a 0 for x in the numerator, we're going to have 2 minus 0, aren't we? So we're just going to end up with a 2 on top. Okay? But still, that's positive. So the second derivative is positive in this middle interval. So that tells us the function is concave up. Okay, so now we need to test in the third interval from 1 to infinity. Now, let's just, I'm going to talk this one out rather than use numbers, but you know you can use numbers. We could put a 10 in there for x, but no matter what's going to happen in the second derivative, see, if we put a value in there like 10, then no matter what, the second derivative is going to be a fraction that has a positive in the denominator. And in this case, we're going to be saying to subtract a real big number, aren't we? When we put 10 in for x, we're going to get 100 when we square it. And so we're going to be subtracting 200. And so clearly we're going to get a negative in the numerator. And if we take a negative and divide it by a positive, then we're going to get a negative result. So in this interval, the second derivative is negative. So we know the graph of the function is concave down. Now, this is kind of like finding relative maximums and minimums when we're looking for inflection points. Inflection points are places where concavity changes, so it's places where the second derivative changes signs. And so we see we have an inflection point at -1, and we have an inflection point at +1. So we have to find the points by finding the y values. Now, and by the way, I'm not going to write down the intervals of concavity, but we can clearly see that the function's concave down on the interval from -infinity to -1, and also from 1 to infinity. Okay, so that really, when I say concave down, it's really kind of the shape that I'm giving there, isn't it? And it's concave up, okay, in the interval from -1 to 1, concave up. And so, you know, that really tells us when we say concave, I don't know whether it's increasing or decreasing, but concave down, we have an idea of what those shapes are like. Okay, so inflection points. Well, for x equal -1, see, that's a place we have an inflection point. The y value would be, we put it into the original function. So we would have the natural log of -1 squared plus a 1. Well, that's the natural log of 2, isn't it? So we have an inflection point. See, this is an inflection point x is -1, and y is the natural log of 2. Now, if we were to approximate that, and this would be for graphing purposes, if we were to approximate that, I put in my calculator natural log of 2, and I got approximately 0.7. Actually 0.69 something, but just to give us an idea, that's approximately 0.7. Now we may have to answer exactly, so we might have to put an answer in -1 comma natural log of 2, but if we were looking at a graph, this is more useful, isn't it? Okay, and so if x is equal to 1, that's the other place we have an inflection point. See, we have an inflection point at this -1, an inflection point at this +1, because we have change of concavity. And so we would put 1 into the function, and we would end up with natural log of 2 again. Natural log of 2. So the inflection point would be 1 comma natural log of 2, which is before, that would be approximately the 0.1 comma 0.7. So let's take a look at this graph. See, we have 2 inflection points and 2 changes concavity. Let's look and see what this particular graph looks like.
Well, here we see the graph, and you can it's clear that we're concave down in this region, concave down in this region, but concave up here. In fact, the inflection points happen at -1, approximately 0.7. So that's looks about right, doesn't it? So this is a point of inflection. That means to the left of this point we're concave down, and you can see that. And then to the right of this point is concave up. And then we have another inflection point at 1,7, and so that's this point. And of course, to the left we're concave up, and to the right we're concave down. And so we found these intervals of concavity, and we see that, of course, that matches the graph, which is no big surprise to us, but it's interesting to see the relationship. Well, that ends this example. We're next going to talk about how the second derivative test can be used to find relative maximums and minimums. Well, so far we found how we can use it to find intervals of concavity and inflection points.